everybody. So in this video we're going to introduce the idea of the matter wave, which is really the beginning of the theory of what we call quantum mechanics, where we treat particles as waves. So again, a little bit of background. We know that the photon is the particle-like nature of light. So light was first modeled as an electromagnetic wave, and with its wave nature we can explain things like interference, diffraction, but we see that there are some phenomena where we have to model light as a particle, a stream of photons. So we've just finished discussing those ideas: thermal radiation, photoelectric effect, Compton scattering, and then Bohr's model of the hydrogen atom. So the whole model of the atom now has this particle-like nature of light built into it, and we get these quantized energy levels in the process. Okay, so what we speak of, let me go to my notepad so I can jot some things down. We speak of, when we talk about light, I've mentioned this before, the so-called wave-particle duality. So wave-particle duality of light. So some phenomena acts as a wave, other phenomena you have to model it as a particle, the photon. And there's a really nice demonstration of this in a picture. Let me show you guys. This is on our course page. We've talked about the double slit interference pattern. Let me slide this over. So I'm going right here. This is a photo from an old book. It's black and white, but it's really cool. So we talked about Young's double slit pattern, right? You send light through two slits and you get these series of bright fringes and dark fringes. And the centers of those so-called fringes predicted by Young with the interference of light. So a big triumph for the wave theory of light. But let me show you in this picture. So what this shows is they set up the double slit experiment, but they do it in extremely low light level conditions, so that what hits their screen, their detector, these little dots, these are actual where single photons are hitting the screen. And again, it's very, very, very low light level. You can see here, this is after 10 seconds. So the light again is overfilling two slits. When it hits the detector, you're getting these dots, and we recognize that, oh, these are photons hitting these pixels. So when the light is hitting the screen, it's definitely acting as particles, right? Photons. And you don't really see much, right, after 10 seconds. But if you wait 10 minutes, look at what you get. Oh my goodness. That whole cascade of photons hitting this screen has actually built up the interference fringes, right? Normally, because we use a lot of light, relatively speaking, as soon as we send light through the double slits, boom, on that screen, you're going to see these bright fringes and dark fringes. And the centers of these, again, are predicted by treating the light as a wave. But we see that this pattern is actually being built up photon by photon. This is really cool. Nice demonstration of the wave-particle duality of light. The only way to explain the interference pattern, the overall maxima and minima, is by treating the light as a wave as it interacts with those slits. Yet we see that when the light hits the screen, it's acting as a stream of photons. This leads to many, many interesting questions. For instance, if you insist that this is a stream of photons for the entire process, you run into problems because you get a question. This is a famous question with the quantum physics. Which slit does the photon go through if you're going to treat the light as a stream of photons? Can you even determine that? Experimentally, you might say, well, let's say you block one slit, and if you don't see the photon exit, you know that it would have gone through that slit, right? The one that's blocked. The problem with that is, as soon as you block one of the slits, this whole interference pattern goes away, and all you're going to see is the single slit diffraction pattern. It's fascinating. Also, if you insist that this is a stream of photons, the whole process, how does an individual photon know where to go, right? And even after the photons leave the slits, you know that when they hit the screen, right, we can see that they're photons. How does an individual photon know where to go to build up this pattern? Again, very interesting questions. So what we're left with is we say, well, light has this wave-particle duality, so when it interacts with the slits, you treat it as a wave. Yet, when the light hits the screen, it's a stream of photons. But that pattern has already been encoded, if you will, because the light acted as a wave when it interacted with the slits. Another way to think about it is you could say that the photons have a probability of where they should go. So photons have a very large probability of going toward to the centers of these bright fringes, and a very low probability of going to these dark fringe areas. Okay, so really cool questions. Now, at the time, with this wave-particle duality of light now pretty much being established by people like Bohr and other people that were working on the photon theory of light and atomic models, people started asking a question. In particular, one guy whose last name is deBroglie, he said, well, in the universe, the physical universe, we have light and matter, or energy and matter, I should say, right? Light is a form of energy. So if we see this wave-particle duality of energy, light, maybe there is a corresponding wave-particle duality to matter. Is that a valid assumption? Okay, so now, up to this point, right, everybody says, well, matter, right, collections of matter, you treat as particles. And that's what we do in regular old physics, right, Physics 1, Physics 2, so-called classical physics. Electrons are particles, right? A brick you can treat as a collection of particles. You can even treat it as one big particle by identifying its center of mass. Okay? Nobody up to this point had seen any wave-like nature to matter. But deBroglie said, well, maybe we just haven't observed it yet, and let's just push the issue. Okay, so the question comes up, well, how do you actually then even define the wavelength of a particle, or of the frequency associated with that particle? So deBroglie puts forth what we now call the deBroglie postulates. And he says, this is how you determine the wavelength and frequency of what we have been thinking as a particle. So the first one, to get the wavelength, what he says is, and I think I want to make sure, be consistent with, oh, okay, I didn't do anything. I thought maybe I put a special subscript, but I didn't. Okay. So how do you find the wavelength if you're going to treat this particle, right? So here's what we normally think of, right, in a picture of, let's say, again, this is an electron, as a particle, right? It has a certain mass, you treat it as a point particle. And it's going to be traveling, right, with some, let's say, speed v, some velocity v. Okay, well, if you're going to treat it as a wave, then, I don't know, it's something like this, right? Sort of like what we do for a photon, right? I don't know how else to draw that. And this thing is traveling, right, at some speed v. How do you define its wavelength? Okay, so deBroglie says, look, let's borrow from the photon. We know for the photon that we can take Planck's constant, right, and divide by the momentum. Because for a photon, if you guys remember, a valid expression for momentum is h over wavelength. So deBroglie says, well, let's just use that. So you can find the wavelength of a matter particle by taking Planck's constant over its momentum, and we know how to find its momentum. I'm not assuming relativistic mechanics here. Okay, we won't for this part of the course. So here's how you would find the wavelength of a matter particle. Okay, Planck's constant over mv, the momentum. And if you want to find the frequency, again, we'll borrow from the idea of the photon. Remember, for the photon, the energy of a photon is hf, right? So what you do is you just take the energy of the particle and you divide by h, and that should find determine the frequency of the particle. Okay. Now I want to focus on the wavelength because nobody again really worries too much about the frequency. We like to visualize wavelength. Okay, and let's see what sort of lengths are we talking about. All right. So you can take. In fact, let me go to the summary notes. I'll show you guys. If you look in the summary notes right here, whoops, I want to do this example. We're going to find the matter wavelength, sometimes we call that the de Broglie wavelength, of a softball. So 8 ounces, and let's say somebody throws it at 40 miles per hour. Okay, and what we want to find out is what is the wavelength, the matter wavelength, if we're going to treat that as a matter wave instead of as a particle, right? The center of mass of the softball, you can think of all the mass being there, so you could think of this even as a point particle. So we could do that calculation. So let me scroll down. And if we take, so our mass is 8 ounces for our softball. And you can convert this to MKS. Oh, I don't have my you know what? Let's do this. I could look this up in my notebook, or we could we'll use the good old Google. So I want 8 ounces to kilograms. So there we go, 0.227 kilograms. Okay, so that's about 0.227 kilograms equals 0.227 kilograms. And how fast did we throw it? I think we said 40 miles per hour, right? Let's double check. Yeah, 40 miles per hour. So again, what we'll do is let's use our friend here. 40 mph to meter per second. I want to use SI units. Oops, I misspelled that. Okay. So there we go. We have about 17.9 meters per second. So that's about 17.9 meters per second. I want to use SI because my Planck's constant I know with SI units. So we can treat, supposedly, the softball as a wave where the wavelength would be h over mv. So we have 6.63 times 10 to the minus 34 joule seconds over 0.227 kilograms times 17.9 meters per second. And you can do a unit check, but you will get meters, and you end up with a value that is about 1.6 times 10 to the minus 34. So we have about 1.6 times 10 to the minus 34 meters. Now, that, my friends, is an extremely short wavelength. In fact, that distance is so small that it is undetectable. It's on the order of what's sometimes called the Planck Length. So some cosmologists, people that model the universe, say that space-time itself is quantized. It comes in discrete lumps. And this would be approximately the size of a space lump. So what I'm trying to say is there is no experiment we can think of that would be able to measure or observe a wavelength this small. Right? So this might be why we've never even been aware of the wave-like nature of matter, because ordinary objects, their matter wavelengths are just too small to observe. There's no interaction where the wave-like nature is apparent. So we always treat it as a particle. Now, this was our softball, right? Which has a relatively big mass. But let's do the similar calculation for an electron. And I know the mass of the electron is 9.11 times 10 to the minus 31 kilograms. And let's say that it's moving at what? Let's go back to the summary notes. 1,000 kilometers per second. So 10 to the 6 meters per second. 1,000,000 meters per second. Which is actually not even that fast for an electron. Okay, so, but we can definitely get electrons moving like that without too much trouble by accelerating them with electric fields. Okay, so look, you do the same calculation, right? You're doing the exact same thing, h over mv. What you'll find out when you put in these numbers into your calculator, you'll get about 0.73 nanometers. So this is going to be 7.3 times 10 to the minus 10 meters, which is about 0.73 nanometers. Or it's about 7.3 angstroms too. You could just use 10 to the minus 10 meters as the angstrom. Okay, now this is also a very small wavelength. However, it's not so small that it's undetectable. For instance, you're on the order of atomic dimensions. So perhaps electrons interacting with atoms, there will be a wave-like behavior to the electrons that can be observed. And in fact, we do observe this, and this is directly analogous to sending light, right, through a diffraction grating. You can send a stream of electrons through a very thin foil. The electrons will interact with the atoms, but the size of the atoms and the spacing of the atoms in the metal crystal is such that the electrons will basically diffract. Very similar to X-ray diffraction, in fact. You can get electrons to diffract. And now what we mean by that is it's analogous to the double slit. This is that thin foil. Here comes my beam of electrons. What you observe is that some electrons will go here, some will go here, some will go here, right? You build up a pattern of where the electrons are hitting. This pattern, and the number of electrons you can think of as analogous to an intensity. So you'll get more electrons here, no electrons here, some electrons here. That distribution of electrons you can think of as an intensity. Well, that intensity pattern is exactly what you would get if you treated this as the diffraction of a wave, similar to an X-ray, where the wavelength of the wave is the deBroglie, or matter wavelength of the electron. So the electron itself is exhibiting a wave-particle duality. When it interacts with these atoms in this metal, it's acting as a wave that is diffracting. But when it's hitting, when the electrons are hitting this observation screen, they are particles hitting this, because you can see the pattern getting built up as each electron hits a different place. So this is direct evidence of wave-particle duality of matter. So we do have experimental observations. Electrons will do this. Any particles where the wavelength is big enough, atomic dimensions, you can observe diffraction. This is neutrons have been observed to diffract in a similar fashion. Okay. Now, these particles that have this observable wave-like nature, they're going to have to be really tiny. Okay, they're going to have to be tiny because they have to have a really small mass. Conventional objects like softballs and bricks and cars, you and me, the mass is just so big that our matter wavelengths are going to be exceedingly tiny, unobservable. But particles like electrons and neutrons, protons, muons, even atoms themselves, they can exhibit wave-like nature. All right, so we have experimental evidence looking at diffraction and interference patterns formed by these particles. Okay, so the idea that deBroglie postulated that there's this wave-particle duality of matter, it is true. We see experimental evidence of it, and this really opened up everybody's eyes to this whole subatomic world, right? Where things sometimes have to be treated, things meaning particles, sometimes have to be treated as waves. And we call that quantum mechanics, where you're treating particles as waves. That whole new branch of physics we call quantum mechanics. It all started, though, by considering light, and then it moves on to the idea of the matter waves, matter wavelength, okay, the deBroglie wavelength. Okay, hey, I wanted to show you guys one thing before I end this. So this make sure, look in the summary notes, make sure you know how to calculate the deBroglie wavelength of a particle. Don't worry so much about the frequency because we're always more interested in the wavelength. All right, similar to this example we just did. Okay, but I want to show you guys one thing, why deBroglie thought he might be onto something. And this was around the time of the Bohr model. You might recall that when Bohr put forth the model of the hydrogen, the condition that determined the stable orbits was the orbital angular momentum was equal to an integer times h over 2 pi, right? That's what he assumed, okay? Now, what deBroglie recognized was, there's my positively charged nucleus, which we now know is a proton. Here is my electron, let's say. Let's say that that's the ground state, right? So this is n equals 1. All right, so what he did is he said, look, if I treat this electron interacting with this positively charged nucleus not as a point particle, but as a wave, then the electron's wavelength would be h over mv, right? Okay, so watch this. I can take this mv, solve for this mv, and I'm going to get h over the wavelength. Now again, this is the wavelength of the electron, treated as a wave. I'll put a little subscript e. So let's put this expression in there, Bohr's fourth postulate. So if I replace mv with h over the electron's wavelength, I'll get h over lambda times r equals nh over 2 pi. And if I solve this for the wavelength, see how Planck's constants they cancel? Let's just cross multiply. We'll get 2 pi r equals n wavelength of the electron, right? So the wavelength of the electron times an integer is 2 pi r for a given orbit. So if n equals 1, right, I find out that the wavelength of the electron is 2 pi r. Now what's so special about 2 pi r? It is the circumference of the orbit. Ooh, the wavelength is exactly the circumference. Look at what happens for n equal 2. Now you find out you get the wavelength, right, times 2 is, oops, oh, that's my Amazon purchase. My wife's Amazon purchase. Anyway. Okay. Look, you get 2 times the wavelength is 2 pi r, which again is the circumference. So what he said is, oh look, in the first excited state, the wavelength of the electron is exactly half of the circumference. So 2 wavelengths of the electron fit perfectly in the new circumference. If you look at n equal 3, 3 wavelengths fit perfectly in the circumference of the second excited state. So in fact, what he's showing is that what determines these stable orbits is where you have the wavelengths of the electrons times an integer fitting perfectly into the circumferences. Another way of thinking about it is the wavelengths, right, fit perfectly into these bigger and bigger circles. Ground state, 1 complete wavelength. First excited state, 2 wavelengths. Second excited state, 3 wavelengths. This is analogous to what is known in physics as a standing wave condition. And this harkens back to waves on a string. You will get these resonances on a string. If you fix a string at both ends and start vibrating it, right, you can get one mode called the fundamental mode where the string goes back and forth like that, okay, with a nice big amplitude. That's what you normally get. If this distance is L, in this case, the wavelength, half of a wavelength, fits perfectly in L. You can get what's called the next harmonic, where you have what is called a node in the middle of the string. If there are any guitar players, you learn how to play higher harmonics. You can actually force a node in the middle of a guitar string. I don't think this sounds too good, but you can do that. This actually might sound okay because it's double the fundamental. But in this case, you find out that the wavelength fits perfectly in L. The next higher mode, you'll find out that the wavelength, right, is exactly 2L over 3. You get a standing wave condition of the wavelength is 2L over n. Okay, that's known as the standing wave condition, where n is your integer. Okay, so these wavelengths fit perfectly in the length of the string. It's up to a half wavelength. Okay, so this is analogous, that you get these resonances. So what deBroglie is saying is that what's so special about these orbits is that the wavelengths, or multiples of the electron wavelengths, are fitting perfectly in the circumferences of the orbits. So this, deBroglie noticed this, and this is why he thought he might have been onto something. We now know that he was, and later people actually observed the diffraction and interference of these particles. So we have this now, this wave-particle duality of matter. Okay, so again, make sure you know how to calculate the matter wavelength of a particle. Next video, we'll talk about this Heisenberg uncertainty principle, okay, which is a neat characteristic of the wave-like nature of particles. All right, that's it. Bye-bye.